What's up, guys? So, welcome to another chapter of system design. And today we'll be discussing a real time live scoreboard system. Now, it's the final over of a Cricket World Cup, and India needs 6 runs off the last ball to win. 1.3 billion people are watching it. The ball is bowled, the batsman swings, and 6. India wins. In that exact moment, every scoreboard app on the planet has to update simultaneously. ESPNcricinfo, Hotstar, Cricbuzz, the official ICC app, 100 million user refreshing at the same second. Now, how do you build a system that handles the sub-second score delivery to 100 million concurrent viewers with zero room for stale data? Now, that is what we are designing today, a real-time live scoreboard system. Welcome to Yoda Monk. And we will go through the requirements, capacity math, the ingestion pipeline, WebSocket architecture, Redis leadership board, and what it actually takes to serve a World Cup final at scale. Okay, let's go into the functional requirement. Let me define the score. We are building a system that, number one, ingests live score events from official data feeds, ball by ball in cricket, goal by goal in football. Second is updates on live scoreboard that all viewers see in the real time, sub-second latency target. Number three is maintains a global leadership board for fantasy sports, who is winning based upon the player performance. Then the fourth is supports live commentary, a stream of text events alongside scores. The fifth is handles score corrections. Data providers sometimes send a correction event. We need to support the rollback. Sixth is it should push updates to millions of concurrent connected clients. Now, the things that are out of scope for this is video streaming, user accounts, fantasy team creation. We are more focused on the score ingestion, storage, and delivery pipeline over here. Now, some of the non-functional requirements are latency. Score update to end user should be under 1 second. This is the hard requirement. The users can see the score on TV simultaneously. If your app is 2 seconds late, users trust it less. Then the throughput. During peak moments, a six, a wicket, a World Cup goal, all clients react at once. We need to handle a spike of tens of millions of concurrent connections. Then availability, it should be 99.99% uptime. A match lasts around 4 hours. If the scoreboard goes down for 10 minutes, that is the catastrophic event. Then we have the consistency, strong consistency for current score. We cannot show different scores to different users simultaneously. The durability, score history must be durable. Every ball, every event permanently logged. Then we talk about the scalability. We must scale for 200,000 viewers for a domestic match to around 100 million for a World Cup match. Now, the elasticity requirement is demanding. We cannot over provision for World Cup traffic year round, but we must be able to scale up in hours of final approaches. Then we come to the capacity estimation. Let's put the number to this. The peak concurrent viewers could be around 100 million for the World Cup final. The score events per matches are roughly 600 balls in a cricket ODI, 10 to 30 events per ball with the commentary, run details, the fielding updates. So around 10,000 events per match. The event size could be around 2 kilobytes each. Now, the inbound event rate is low. The official data feed sends maybe 5 to 10 events per second during an active play. This is not a high write throughput system on the ingestion. Now, this is not a high write throughput system on the ingestion side. The outbound fan out rate. Now, this is the one event, fan out to 100 million connections. At 2 kilobytes per event, this is 200 gigabytes of output data in under 1 second. No single set of servers can handle that. That is why CDN Edge Delivery is the core architecture here. Now, for fantasy sports, let's say 10 million active fantasy users watching the match. Each score event updates the multiple player scores. Each player appears in thousands of fantasy teams. One ball event could trigger millions of leaderboard position changes. Now, Redis Z add throughput becomes the critical metric. With this, we go to the API and the data modeling. The API surface of this system. First, we will have the client facing. The WebSocket Connect client establishes a persistent connection, receives score events pushed in real. The get current score HTTP endpoint returns the current match state used for initial page load and reconnects. The get leaderboard, it returns top K fantasy teams for a match. Then we have the get event history. We have the paginated history of all score events for a match. Internally, we can have a score event API, which is a post type. The data provider ingestion endpoints, which internally we can have an API that is of post type. It could be score event. This is the data provider ingestion endpoint, the official feeds, send events over here. Then we can have a post correction, a rollback, or the correction event. For the data model, we have a match table in which we have the match ID, team, venue, status, pre-match, live, completed. Then the current score as a JSON blob, then last updated timestamp. In the score event table, we can have event ID, match ID, timestamp, event type, ball, wicket, boundary, 6, review, correction. The payload JSON with the full event details, and the sequence number is critical. Every event has a monotonically increasing sequence number. Clients track the last sequence number they receive. If they reconnect, they can ask for all events since sequence N. This handles temporary disconnections cleanly. The leaderboard model. In Redis, we will have the key as the leaderboard colon match ID. Then we will have a sorted set in which there will be score colon fantasy points. Then we will have member colon team ID. Now this is updated on every score event that affects a player in the match. After this, we will go into the high level design. Let me walk you through the architecture. Now on the left, the official data feeds from the sports data provider. The companies like Cricinfo, Sports Radar, Stats Perform, they send events over WebSocket or HTTP push connection. These events land at the score ingestion service. The score ingestion service does three things. Number one, it validates and deduplicates the events. The data providers occasionally send duplicates over here. Number two is it writes the event to the Kafka. Number three is updates the current match state in the Redis. Now Kafka is the backbone. From Kafka, three consumers process the event in parallel. Now consumer one, it does the score processing, which updates the persistent score history in Cassandra. It updates the current match. Now consumer two is the leaderboard updater. It computes the fantasy point changes. It updates the Redis sorted set. Then consumer 3 is the fan-out service. It pushes the event to all the connected WebSocket clients. On the delivery side, WebSocket gateway servers maintain client connection. They subscribe to the Redis PubSub channels per match. When an event is published, it is pushed to all the clients subscribed to that match. Now for the clients not on WebSocket, mobile apps that backgrounded, web clients that disconnected, score updates are pushed to a CDN Edge cache. Those clients poll the CDN on reconnect. Now, this is the architecture. Let's go deep dive. The first component we are going to discuss about the score ingestion and the Kafka pipeline. The score ingestion part is the source of truth. The official data provider has an SLA with us. They guarantee delivery for every ball within 200 milliseconds of it happening on the field. We maintain a WebSocket connection to the feed. Now, this is a persistent, reliable connection. If it drops, we reconnect with the exponential backoff and replay from the last received signals. The ingestion service receives the event. Step 1 is deduplication. We maintain a Redis set for recent event IDs per match. If we have seen this event ID before, we drop it. This handles the data provider sending duplicates during the reconnects. Now, step 2 is validate. We check the event data schema. We reject the malform events. We alert on anomalies like a scoreboard going backward. Step 3 is assign our own sequence number. The provider sequence is their clock. We generate a monotonically increasing sequence using a distributed ID service. Step 4 is write to Kafka. The topic is score events and the partition key is match ID. This ensures all events for a match go to the same partition in order. Now, why Kafka is here? The reason is because we have multiple downstream consumers, Cassandra writer, leaderboard updater, fan-out service. Kafka lets all of them consume the same event stream independently. And it gives us a replay. If the leaderboard updater falls behind, it can catch up from the Kafka's log. We set Kafka retention for 48 hours, long enough to cover any realistic recovery scenario. The next component is the score correction and the rollback. Now, this is the scenario no one wants, but every system must handle. A no ball is called on a delivery that was already scored. Suppose a no ball is called on a delivery that was already scored as a wicket. The batsman is out. The score changes retroactively, or a human error in the official feed sends a wrong score. The provider issues a correction 5 seconds later. Now, how do we handle this? First, the event model must support corrections explicitly. Every event has a type field. Normal events have a type equals ball. The correction event has type equals correction. With a reference to the event sequence number they are correcting and the updated payload. When the score processor receives a correction event, number one, we mark the original event as corrected in Cassandra. We never delete the history. We append. Number two, we recompute the current match state from the scratch, replaying all non-corrected events. Then number three, we write the new current state to the Redis. Number four is we publish a correction event to all WebSocket clients. On the client side, the UI shows a brief score updated indicator when a correction arrives. It replaces the displayed score smoothly. No jarring flicker. For the leaderboard, corrections are harder. A correction may change in the fantasy points awarded to a player in an event that happened 30 seconds ago. We need to subtract the old point and add the new points. Now in Redis, this is two Z increment by operation, a negative increment and a positive increment. We maintain a player event ledger in the Cassandra. For each player, each event, what points are awarded when a correction arrives. We look up the original award, reverse it, and apply the new award. Now, this is an append only ledger. Every adjustment is a new row. The current points balance is computed by summing the ledger. The next component we are going to discuss about the WebSocket delivery architecture. Now, getting scores to 100 million concurrent viewers is the hardest part of this system. Now, let's talk about the transportation option. Option one is short polling. Client ask the server for the latest score every second. This is simple, but 100 million clients polling every second is a 100 million requests per second. Now, this is 1,000 times what we wanted. Then, option two is the long polling. Clients make a request, server holds it open until there are new events. Option two is long polling. Clients make a request, the server holds it open until there is a new event. This is better, but still a very heavy weight. Each long poll is an open HTTP connection, which is hard to scale. Then option three is server sent events. HTTP based one-way stream. Server pushes the event. Then this is simple and it works with standard HTTP infrastructure. Option four is WebSocket. Full duplex persistent connection. Client sends match subscription. Server pushes the event. For a live scoreboard, WebSocket is the right choice. Now here is why. The client needs to subscribe to a specific match. This is a two-way interaction. SSE is one way. WebSocket gives us lower overhead per message once the connection is established, and we need sub-second delivery. WebSocket is faster than polling-based approaches for higher frequency updates. Here is the WebSocket architecture. We run WebSocket gateway servers. There are stateful processes. Each one maintains 10 of thousands of client connections. The gateway is subscribed to Redis PubSub channels, one channel per match. The channel name is match ID. When the fanout service receives a score event from the Kafka, it publishes it to the channel for that match. All WebSocket gateways subscribe to that channel receive it. Each gateway then pushes it to all connected clients. Now a single Redis PubSub publish triggers delivery to every gateway. Each gateway handles its own client. This scales horizontally, and when we add more gateways, it handles more clients. The Redis PubSub broadcast is the only coordination point over here. Now, for 100 million concurrent connection, we need around 10,000 gateway servers, assuming 10,000 connections per server. This sounds a lot, but with auto-scaling groups key to active connection count, it is manageable. Now, the next part is the CDN Edge Delivery. WebSockets work great for clients who are online actively watching. But what about clients on unstable mobile connection? What about clients who background the app? We layer CDN Edge caches on top of the WebSocket architecture. The current match score is also maintained at CDN Edge nodes globally. Every time the score processor updates the current match state in Redis, it also publishes it to the CDN origin. The CDN caches the current score with a TTL of 1 second. Now, the client who cannot maintain a WebSocket connection poll the CDN Edge endpoint. They get the score from the nearest edge node. Now, 1 second TTL at the CDN Edge means the score is at most 1 second stale for the polling clients. This is acceptable. Why not 0 TTL? Because at 100 million clients polling every second, even CDN Edge would be overwhelmed. Now, 60% of the World Cup traffic is the WebSocket. 35% is CDN polling. Now, 5% is the direct origin fallback. We use Anycast routing to direct lines to the nearest CDN edge. This keeps the latency low regardless of viewer geography. During a six or a wicket, there is a traffic spike on both the WebSocket path and the CDN polling path. CDN absorbs the polling burst. WebSocket gateway handles the real-time push over here. Okay, so we'll go to the next component, that is the global leaderboard at scale. So the fantasy sports are a massive business. For every match, 10 million users have active fantasy teams. Each team has 11 players. When a player hits a boundary, millions of fantasy team updates simultaneously. We use Redis sorted set for the leadership board. The key is leaderboard match ID. Z add updates or insert a team score. Z range or Z rev range retries the top K teams. Z add is an order of log n. For sorted set with 10 million members, this is about 23 operation. That's very fast. But here is the right problem. A single ball event might affect 4 players. Each player is in an average of 200,000 fantasy teams. That is 800,000 Z-ad operations per ball event. At 10 events per second during active play, this is 8 million Z-ad operations per second. Redis can handle 1 million operations per second on a single node. So we need to shard the leaderboard. The sharding approach is we split the leadership by team ID hash 16. This will account to around 16 shards. The Z add for a team goes to shard hash of the team ID modulo 16. To get the global top K, we query the top K from each shard, then merge and rerank. This is the top K merge problem. 16 shard times 1 million Z add per second, each equals 16 million operation per second capacity. That covers our requirement with the headroom. Now for the global top K query, we run priority queue, merge across 16 shards. Each shard returns its top K. We heap merge them. And the final result is the global top K. For K equals 100, this is fast. 16 queries, each returning 100 rows merged in the memory. Okay, after doing the deep dive, this is one of the most important section, that is the observability and monitoring. Now, for a system serving World Cup final, observability is not optional. Some of the key metrics are the score, event, end-to-end latency, time from data provider sending to this is the time from data provider sending the event to it appearing on the client screens. P50, P95, P99, alert if P99 exceeds 800 milliseconds. Then we have the WebSocket connection count. That is about the active connections per gateway server. Alert if any server exceeds 80% capacity. Then we have the Kafka consumer lag for each consumer group. The fan out service, the leaderboard update if the lag exceeds 1000 messages. The Redis leaderboard operation latency. Z add, Z range, P99. Alert if Z P99 exceeds 5 milliseconds. The CDN cache hit rate. During a match, this should be above 99% for the current score endpoint. Error rates on any 5xx on the inbound provider feed triggers an immediate alert. Now for the World Cup, we run a game day readiness check. 2 hours before the match starts, we simulate load equivalent to 15 million concurrent viewers against our staging environment. We verify auto-scaling response within 5 minutes. We verify all monitoring alert triggers correctly. We have a runbook for every known failure mode. Now, on-call team during a World Cup final is 6 engineers, 2 on ingestions, 2 on delivery, and 2 on leaderboard, plus a senior engineer as the incident commander. All right, let's bring it all together. We built a real-time live scoreboard that ingests score events from the official data feeds through Kafka. It processes them with strong consistency and supports correction with full audit lineage. It delivers the score to 100 million concurrent viewers via WebSocket Gateway, Redis PubSub, and CDN Edge all under 1 second. It maintains a sharded real-time leaderboard using Redis sorted set across 16 shards. And then it scales proactively for scheduled events like a World Cup final. The key insight in the system is the layered delivery architecture. WebSocket for real-time precision, CDN for scale absorption. CDN handles the long tail of clients. The WebSocket handles the client who needs sub-second precision. Without that layering, you simply cannot serve 100 million viewers, no matter how many WebSocket servers you throw at it. Now, if this was valuable, subscribe to Yoda Monk. We cover real-time systems, real scale, real trade-offs. See you then.